Hello, Ms. Oshner. This is Adam Shamoon for my week 12 or chapter 12, week 4 videos on intro to calculus. So I'm just going to start off. I'm doing question number 37, 38, 39. So I'm just going to start off with defining a limit. So a limit describes the value of a function or a function approaches as its input approaches a certain value. Okay. And so now, using what we know about limits, I'm going to show limit notation and describe generally all the parts of it. So the limit, so limit notation looks a lot like this. So limit as x approaches a of f of x equals c. So a is our input value, and our input value is located on the x-axis. F of x being our function, and c being the output value that's essentially the c value is the alpha value that we're trying to solve for in this case. So I just need to define a few more things about limits, and then we can go ahead and get started on this problem. So just to give a brief overview, there are three types of limits. So first, let's start off with a right-hand limit. So a right-hand limit looks like this. The limit as x approaches a plus of f of x equals c. So all the parts are basically identical and the same, except for this plus right here. So the plus describes and really tells us that there's um, the x variable is approaching from the right side, and that's why it's called a right-hand limit. So the limit approaching from the right side uses this plus right here. And so for our left-hand limit, we'll have x approaches a minus f as f of x equals c. And so this minus indicates to us that this is in fact a left-hand limit, and that makes the distinction from a right-hand limit. And so a general limit describes the behavior of a function as its input approaches a specific value. So it's the same as the general limit, or it's same as what we define limit as up here. A general limit is essentially where RHL, the right-hand limit, equals the LHL, where the two limits meet. So, for example, if we can draw a little function over here, just to show what a limit actually looks like. So this would be the ideal case scenario. So let's just pretend that we don't have an x value at 3. So there's a removable discontinuity there. So as x, so the limit as x approaches, and then our y value can be 4, as x approaches 3, f of x equals 4. But what you'll also notice is that the limit as x approaches 3 minus, so our left-hand limit, we notice as the x values get greater, we get all the way to the point of, as our x values approach 3, we get closer and closer to 4, also equals 4. And the limit as x approaches 3 plus, so from the right-hand side, we notice as our values get smaller and smaller, closer to 3, our y values will get very, very close to 4. So basically, this confirms to us that when the right-hand limit and the left-hand limit are equal, there will be a general limit at the value, at the f of x value that they're equal at. So understanding all this information, we have to get started with the problem now. So to get started here, we can already recognize that we're gonna try to solve the right-hand limit for the problem here because we see the plus sign by the 0. So that indicates to us that we're finding a right-hand limit. And so what we can do to figure out which one of these equations, so if we're going to use the first one or the second um, one or two, to find the limit for the from the right hand side, what we're going to do is we're going to look at the domain restriction. So the domain restriction here shows that x is greater than 0. So when x is greater than 0, that's going to be our right hand limit. So given that, f of x equals x minus 3 when x is greater than 0, because this is our right hand limit. It's approaching from the right hand side. And so what we're going to do is we're going to set up limit notation. The limit as x approaches 0 plus of f of x equals x minus 3. And what you can do to solve um, for limits like this is we can use direct substitution when it's continuous function. 0. So we're going to substitute 0. So you basically just sub in the a value as x. And so f of 0 equals 0 minus 3. The limit as x approaches 0 plus of f of 0, or of f of x, equals negative 3. Okay, so this is our right-hand limit. Again, because it has the plus sign, but also we know that because of the domain restrictions, when x is greater than 0, that is going to be our right-hand limit. Next, for our left-hand limit, we are going to start, and since we already use this equation, we know we're not going to use it, but just to check, we know that when x is less than or greater than, or less than or equal to 0, we know that that's going to be our left-hand limit, just by the domain restriction that applies. That's going to be approaching from the left side. And so what we're going to do now is f of x. We're going to take that part of the function, f of x squared, or f of x equals 2x squared plus 2x plus 1, when x is less than or equal to 0. And so this function is also continuous, so we're going to do the limit as x. And by the way, we just knew that both these functions were continuous because they didn't have a denominator that would exclude any x values. So as x approaches 0 minus, because this is the left-hand limit, we can tell that by here. We know that when as a minus sign, it's a left-hand limit. So as the limit approaches 0 minus, f of x equals 2x squared plus 2x plus 1. The limit as x approaches 0 minus, we're going to use direct substitution. So we're going to plug in our a value for our x equals 0 squared plus 2 times 0 plus 1. And so 2 times 0 squared is going to be 0 because 0 squared times 2 is 0. 2 times 0 is also 0, and then we're just going to have plus 1. The limit as x approaches 0 minus of f of x equals 0 plus 0 plus 1. The limit as x approaches 0 minus, this is f of 0, of f of x equals 1. So this is going to be now our left-hand limit. Okay, so now we don't see a mark here, so we know that we're finding our general limit. So what we're gonna do is our general limit equals where or happens to be where our left-hand limit and our right-hand limit are equal. So let's bring our left-hand limit over here. So the left-hand limit is x approaches minus f of x equals 1. And then our right-hand limit as x approaches 0 plus f of x equals negative 3. So since our left-hand limit and right-hand limit aren't equal, there will be no general limit. So no GL is our answer. And so just if we wanted to understand this a little bit better, um, the reason why we wouldn't have a limit here is because there's a jumping discontinuity. When the y values change so like with such volatility, there's not going to be a limit because the x value is going to be approaching from a totally, or the right-hand limit is going to be approaching from a totally different y value than the left-hand limit. So because there's such a gap, that's called a jumping discontinuity, and that means that there's no general limit or no place like up here. when I drew the function, um, when there was a hole right here, the x values approach from both sides. But if there's a jumping discontinuity, like a value here and a value here, or a value here and a value here, then there's only gonna be a right-hand limit. So you see as it's approaching from the right, it's looking like f of x is about -2, and when it's approaching from the left, it looks like f of x is just about +2. So there's not gonna be a limit here because the left-hand limit and the right-hand limit aren't equal to each other. This is a jumping discontinuity because it changes with such volatility. All right, thank you so much for watching. Just to summarize the answers, uh, here's the answer to 37, here's the answer to 38, and here's the answer to number 39. Thank you for watching.